let's start right away. Welcome everyone. In this talk, we will discuss how to fit a simple body model to images using optimization. To understand human actions, we need to estimate the configuration of people from camera images. For this, we need to estimate their 3D body, shape, and pose. In more technical terms, as input, we get a single RGB image of a human without any information about body pose, scene structure, or camera calibration. And as output, we wish to obtain the body shape and pose in full 3D. In the deep learning era, the ideal solution probably sounds like a deep network that directly maps RGB pixels to simple parameters in a fast and robust way. However, for this we need good training data with ground truth information. And the problem is that there is a lack of datasets that pair in the wild everyday images with 3D bodies. And the reason for this is that annotating full 3D bodies is intractable for human annotators and does not scale up. Luckily, there is a solution to this based on 3 pillars. First, traditional optimization-based methods need no training. Second, in contrast to 3D, 2D body joints are easy to annotate. Deep learning models, like OpenPose, can robustly detect 2D joints in images. Third, generative models like SMPL function as a strong prior by capturing the statistics of 3D body shape across a big human population. All these come together in the Simplify project presented at ECCV 2016. Simplify builds on body joints. SMPL has the 3D body joints shown with blue color, lying under its 3D mesh and are used for articulation. These joints are regressed from the shape parameters beta and pose parameters theta. These are used by a data term that measures the 3D joint reprojection error, which we need to minimize. Under the hood, things work like this. First, we estimate 2D joints in the image using deep cut or any other similar 2D joint detector. Second, we start with an initial configuration of SMPL that has the 3D joints shown with blue. And then we project the 3D joints on the 2D image plane with an estimated camera and measure the reprojection error. We need the projected 3D joints to ideally match the detected 2D joints. However, initially this is not the case. To achieve this, we use gradient descent to find the most likely simple model configuration that best explains the detected 2D joints. For this, we jointly optimize over simple model parameters and camera parameters. Here, please notice how the final simple configuration matches the input image. This is a simple and effective idea. However, it doesn't always work that well. Sometimes joint detection is noisy and there are missing joints or side flips. And these result in implausible estimation as we see here. And please notice the extreme self-intersections. To penalize this efficiently, we approximate a body mesh with a set of 3D capsules. And using this, we penalize self-penetrations. And as a result, we get much more natural poses. Another important problem is that color images have no depth information. Consequently, there are strong depth ambiguities. In this example, we see that knees are bent, although they shouldn't. And to account for this, we really need good priors. For pose, we use a Gaussian mixture model learned on the CMU mockup dataset. And for shape, we use the PCA, shape space of SMPL, that captures the shape statistics across the human population. We combine all these terms together with some regularizers in a single objective function epsilon. And we minimize this energy with gradient descent. And for this, we can pick up your favorite optimizer. We apply Simplify on in-the-wild datasets like LSP. Here with blue color, we fit a neutral simple model, while with pink color, we fit a gender-specific simple model. Results show that Simplify estimates reasonable simple bodies that look realistic and agree with the input image. However, there's an important limitation. Estimated bodies have always neutral, unexpressive faces and flat, non-articulated hands. We account for these limitations in the Simplify X project presented at CVPR 2019. For this, we first built Simple X, an expressive statistical whole body model that goes beyond simple by having well-articulated hands and an expressive face. Generally, this approximates the homunculus model by giving higher modeling capacity to body areas the brain thinks that are important for communication and interaction. Simple X also has a new shape space that better captures correlations among body parts. We then follow the simplify recipe, but extend it for the whole body to include hands and faces. First, we use open pose to detect whole body 2D features in the image. And then we use Simple X and project its 3D joints on the image plane. And finally, we minimize the reprojection error like Simplify. This faces similar ambiguities like Simplify. Due to the lack of depth information in color images, it is hard for our method to figure out if the arm needs to be in front or behind the torso. To better account for this, we employ recent advances in datasets and deep learning. We employ the AMAS dataset that provides full 3D meshes for a big collection of mockup datasets. And with this, we train a variational autoencoder that learns a low-dimensional latent space Z. This is the manifold of valid body poses. And now our optimization takes place on this manifold instead of the full pose space. This manifold accounts for many ambiguities, but cannot capture anatomical limits. As a result, our estimated poses might still have self-penetrations, as we see here between the elbow and the knee. We account for this with a much more accurate method that operates on the original meshes instead of rough 3D captures. For efficiency, we first find the colliding triangles that are highlighted with red color, and then we define local 3D distance fields only for these triangles. For each distance field, we find the penetrating vertices and we penalize them according to the depth of penetration. This term is implemented as a fast CUDA kernel and is differentiable. We combine these terms in an energy function epsilon, and this looks similar to Simplify, but with all terms updated. This is a visualization of the optimization convergence from the initial template to the final configuration. And please notice that the video is sped up for visualization purposes. The final result looks realistic. However, for the same 3D joints, 3D shape is highly influenced by gender. Looking at mesh registrations for big datasets of human scans, we notice that male and female bodies follow a different distribution. We therefore train a classifier that predicts a gender label for the input image. And when the classifier is very confident, we use the respective gender-specific Simple X model. In the opposite case, we use a non-binary gender-neutral Simple X model. We apply Simplify X on several in-the-wild datasets like LSP for sports scenarios, MPII for everyday actions and hobbies, and expressive images that we find on the web. In these examples, please notice the gestures for the sign of victory, the surprise expression, the tension, and several other expressive states. These results look good, but there are a few limitations. First of all optimization-based methods depend on good initialization. Simplify and Simplify X use a heuristic that triangulates the 4 torso joints, namely the shoulders and the hips. When the torso plane is almost vertical to the camera plane, the heuristic fails and optimization gets trapped in a bad local minimum, as we see in this example. Second, optimization-based methods tend to be slow. Simplify X needs roughly 1 minute per frame, and this is not ideal for real-time applications or scaling up to huge data. Finally, Simplify and Simplify X reason about bodies in isolation from the world. We tackle this with a PROX project presented at ICCV 2019. Simplify X estimations look reasonable, and in this example, the estimated yellow vertices fall more or less on top of the right RGB pixels. To test how this complies with a 3D scene, we use an off-the-shelf RGBD application to get a 3D scan of the room. We then register the estimated human mesh and virtual camera to this. And as a result, we see that the estimated human mesh heavily penetrates inside objects. And obviously, this is not realistic. To account for this, we use joint reasoning for both the human and the scene. This sounds like a more challenging problem, but the intuitive physics of contact actually make the problem easier. More specifically, here we're based on 2 pillars. First, 2 objects cannot share the same space, therefore they cannot interpenetrate. Second, for interactions, we need different surfaces to come in close proximity and contact each other to apply forces. For this, we present a method called prox that stands for proximal relationships with object exclusion. In this example, prox estimates the gray mesh, which is much more realistic. And please notice how the strong penetrations are gone, while there is contact at all the places where you expect contact to occur. For example, between the human's back and the sofa, the arm and the armrest, and the feet and the floor. To achieve this, we built on SimplifyX, and we extend it in two main ways. First, instead of penalizing only self-penetrations with local 3D distance fields, we need to also penalize big penetrations of the body into walls, furniture, and floors. And for this, we employ a global 3D distance field that represents the entire room. Second, we manually annotate all the vertices that are shown with blue that are the most likely vertices to come in contact with big objects. And then, when the blue vertices are in close proximity to seen surfaces, both in terms of distance and orientation, we encourage them to snap onto the scene. In practice, we get the energy function of SimplifyX and add one term for penalizing interpenetration and one term for encouraging contact. And really, this is the beauty of optimization-based methods. They can be extended fairly easily with no need for retraining. First, we design some good terms, and then we simply add them to our energy. When the input includes a depth image, we optionally add a depth fitting term to boost accuracy. We call this variant prox-D, while the baseline that keeps the depth term but removes the two contact terms is called SimplifyXD. After designing the prox method, we go around and we reconstruct 12 everyday rooms like offices, bedrooms, dining rooms, and so on, and capture 20 people performing everyday activities in them, like reading a book, lying on a bed or sofa, sitting on chairs, writing on a whiteboard, or simply having fun. And this provides a unique dataset of human meshes interacting with good accuracy with rigid 3D scene meshes. This dataset has been key for recent methods that learn how to populate an empty scene with humans that realistically interact with it. And a later session today will discuss more methods for this application. However, contact does not take place only between humans and objects. Self-contact is equally important. For example, people touch their faces 23 times per hour. Moreover, they cross their arms and legs, they put their hands on their hips, etc., either to get physical support or to convey their emotional state. Despite its importance, self-contact has been mostly ignored in the literature, and this is for a good reason: the lack of appropriate datasets. This project accounts for this in multiple ways. First, it presents 3DCP, a dataset of 3D meshes with self-contact in simple X topology. For this, the authors scan 6 subjects in various self-contact poses and register the simple X model to the scan using a self-contact preserving energy. They also search the AMAS mockup dataset for near-contact poses, as we see with orange, and refine these poses to encourage self-contact and resolve self-penetrations, as we see with blue color. These 3DCP meshes are interesting, but they lack color images paired with them. To collect such in the wild images, first, the authors rent synthetic images of 3DCP meshes and highlight the contact areas as we see with blue color. Then they ask users on Amazon Mechanical Turk to mimic these poses and have someone get a photo of them while mimicking. The users mimic the poses reasonably well, but not perfectly. For example, here, please look at the hand position on the left and the global orientation on the right. To correct for these differences, the authors introduce SimplifyXMC, which extends SimplifyX for mimicking contact. SimplifyXMC takes into account the presented pose and contact areas, as well as the subject's height and weight. The latter contribute to better body shape estimation because this is important for contact. The method also introduces two contact energy terms, namely LP, that pushes vertices that penetrate inside the mesh towards the surface, and LC, that encourages contact between vertices that are outside but close to each other. And here are two examples. At the left, with blue color, we see the poses for mimicking that are presented to the users. At the middle, we see images of the mimicked poses. And at the right, with gray color, we see the Simplify XMC feeds for these images from various viewpoints. Simplify XMC provides unique data for training a regressor, as will be discussed in the next session today. In a nutshell, in this presentation, we discussed about Simplify, that fits simple to body-only 2D joints. Simplify X, that fits simple X to whole body 2D joints. Simplify XD, that extends Simplify X to also use depth. Prox, that extends Simplify X with human scene contact constraints. And Simplify XMC, that extends Simplify X with mimicked self-contact constraints. And for more details about each project, namely the paper, the models, and the code, please visit the respective website. So thank you for your attention. And now I will hand over to Timo for the second part of the session.
Actually, could we take a few questions? We've got some questions in the chat that have been building up.
I can maybe start sharing the code the presentation meanwhile.
Okay.
Right. Naureen, did you have a list of?
Yeah. Could you wait? So how sensitive would this be to estimated camera parameters? Frank Yu was asking this question.
Yeah, and in the original Simplify, you said we estimate camera parameters along with the poses. How hard is that?
I didn't hear the question well. Can you repeat?
Yeah, it's really about estimating the camera parameters in Simplify. So in this case, I think the camera parameters were quite, this was basically a scale. It was scaled orthographic, if I'm not mistaken, but maybe it was perspective, I don't know. So if it was...
It's a weak perspective model, and we assume that the focal length is roughly known. Basically, the assumption is that when we observe full body images, there's a certain focal length that is very likely. And this is what we use.
And there's also a question about V-poser, how the weights of the KL term and the reconstruction terms are found, how sensitive the model is to such weights of the V-poser.
I think the models, the weights are found empirically. Of course, Nima can jump into this if he wants, but really all these things involve a lot of eyeballing. So basically you get into the ballpark and you refine the weights according to what looks realistic. In this field, there is no huge data set that you can use for evaluation for validation to set your, to tune your weights and so on. So really everything depends on having things look realistic.
And then there's a question about the optimization time for Simplify X. How long does it take?
So it takes roughly 60 seconds. And this is including all the little tricks that we have, including the CUDA kernel for the self-intersections and the PyTorch implementation. For example, the PyTorch implementation gave us a speed up of 8 times compared to our old optimization framework. But with all the tricks combined, we roughly need 1 minute per frame.
So they're also asking about what kind of computers. I think that's just as long as it can run CUDA, right? That's the only...
Yeah, I mean, a reasonable desktop computer with a decent GPU.
And there's a question whether we assume that the 2D key points are ground truth. No, they're computed by, for example, OpenPose. So they're noisy, and that causes problems.
And different models come with different noise, right? One should expect this.
These two-step methods where you first estimate one thing and then estimate out something else from it, always a problem because, you know, the first stage makes a mistake. But OpenPose is actually pretty good. It's surprisingly powerful and strong. So.
But really, the important thing is, as you said, the joint detection is a bottom-up model that will always be noisy. And the top-down model, which is simply kind of denoises things a little bit.
But that kind of leads us into the next presentation by Timo. So thanks, everybody, for the question.